Hello everyone, my name is João Parente, and I'm going to give a short presentation about fatigue behavior of 3D printing auxetic materials, basically an overview. So what are auxetic materials? Auxetic materials are a type of mechanical metamaterial, have a negative Poisson ratio. This means that when the material is stretched, it expands in the opposite direction, and the opposite occurs during compression. This can be used in several applications, such as energy absorption and strength sensors. Research of this type of materials is still in the early stages, but there's a great potential for this type of works of materials. The research of this type of materials in terms of fatigue may lead to the creation of new types of auxetic materials with improved mechanical characteristics. So the type of auxetic material can be determined by the geometry of its structural cell. So here are the most basic structures. First, you have re-entered, which on the left, which basically is a hexagonal structure. And when this material is stretched, the sides that are facing inward expands and then and thus make the material more thick and stronger. The second most used type is chiral structure, which is a circle with several 3 or more arms. That when this material is stretched or compressed, the center circle moves and then makes the material stronger. And the other types, we have a rotating rigid structure, arrowhead, star-shaped, and S-shaped structures. So there are several fabrication methods. Some we'll talk about here. Fused deposition modeling, selective laser sintering, cutting and laser cutting, and mechanical and milling processing. So this can be used in several applications. For example, I have here a few types in footwear, footwear that is more beneficial in terms of energy absorption, in sports equipments, for example, for protection, for example, in automotive components for the creation of lighter and stronger materials, in medical devices for stents that compress or expand depending on the blood pressure, in aerospace applications, materials that can change shape depending on the compression or expansion, and robotics for use in harder surfaces. So taking this into account, our objective was to provide an overview of all works available concerning fatigue and understand and compile the main conclusions about this type of material in terms of fatigue behavior. So when we looked at the literature, we had a problem. We found that there were hundreds of articles concerning auxetic materials, but almost all of them focused on the flexural, tensile, and compression behavior of these materials. And we looked at the fatigue behavior. We only found 19 articles, of which 10 of them, about half of them, were about 3D printing. So starting with those works, there were only 10 articles, which you can see here. The first article was only published recently in 2018. In between all the materials, the main materials was PLA, followed by shape memory polymer, thermoplastic polyurethane, aluminum alloy, and titanium. In between the geometries that were used in these works, there were re-entered, S-inch, and chiral geometries. And the types of fatigue studies were in compressive, tensile, and 3-point bending tests, fatigue tests. So the main conclusions. So looking at these works, we found out that 3D printing was a very promising fabrication method for use in this type of works, since it allowed the creation of difficult or even impossible structures that were difficult to produce using traditional cutting methods. And we also found out that within all these works, all of them show that 3D printing auxetic structures had a longer fatigue life compared to the non-auxetic structures. We also concluded from these works that the main that the auxetic fatigue life of these materials was dependent on several works, several factors, including geometry of the material, mainly the Poisson ratio, the material properties, and the loading conditions that were applied during testing. Concerning printing in itself, printing parameters were also a very important factor since uniform structures have better fatigue life results than materials that were printing in a non-uniform way. But we also found problems, mainly the creation of residual strain and stiffness degradation after repeated testing. But some works concluded that fatigue performance of these structures could be improved by optimization and design manufacturing through computer simulation. Since these were very few works, we also studied the other works that did not use 3D printing, since this information could also be applied in 3D printing. So there were 9 articles that studied this fatigue. It did not use 3D printing. These works, the first was published in 2006, and as you can see, almost all of them focus on aluminum alloy, with 2 focused on polyurethane foam. These works focused mainly on reentrant and chiral geometry, and the fatigue tests included compressive, tensile, flexural, and crack propagation fatigue tests. So adding the conclusions from these works to the other ones, you can also add that the orientation of the unit cell, as well as the type of auxetic structure and the presence of defects, in this case in the metal, could also improve the fatigue life of the material. And some works also concluded that chiral geometry had better fatigue life compared to reentrant structures in terms of fatigue life. Other works also concluded that fatigue, the auxetic structures had the ability to delay the crack initiation and spread the damage over a larger area, and that is the damage that occurred mainly on the corners of the individual cells, and then propagates depending on the orientation of the cell and the loading conditions. So to conclude, so auxetic structures can provide an improvement in terms of fatigue behavior compared to non-auxetic structures. The geometry of the material properties, and the loading conditions were very influential in the fatigue life of an auxetic material, but there's still a need to further study this type of behavior in terms of in these types of structures, mainly for now the cell geometry, since mostly of these works focus mainly on one type of cell geometry. And these studies, of course, will further help us understand the fatigue life of this material and help us create better materials. So I'd like to thank SIMAS and EBI for this work. And here are the references for the works that I used in this work. So that is all. Thank you.